Good afternoon, dear students. Today we will continue talking about the mechanisms of separation. So far, we mentioned one of the separation, size exclusion. Okay, if you remember, we said that size exclusion is the same mechanism. It has many names, such as gel permeation and molecular sieve mechanism. Okay. Now, the idea of separation, according to size exclusion, that the large molecule will elute before the small molecules. The reason that the small molecule will take longer time in passages inside the particles and the pores inside them, whereas the large molecules will get through the column only through the interparticulate pathway. Okay? And it is good for separating proteins from the tested drug because we have a substantial difference in terms of molecular weight between the proteins and small drugs. So, in order to gain such mechanism, you have to have a substantial difference in molecular weight. Otherwise, size exclusion will not be encountered, and it cannot be considered as a mechanism of separation. As we said, unless we have substantial difference in terms of molecular weight between the two analytes. The second mechanism is adsorption. Okay. Now, adsorption is the main mechanism for normal phase silica, and adsorption will rely exclusively on the direct physical interaction between solute and the adsorbent surface. For example, when we have silica, okay, silanol can form hydrogen bonding with some of the analytes, but not the others. For example, if we have one of the diols, such as resarcinol, which can make hydrogen bonding with silanols, and another compound, let us say benzene. Now, definitely, resarcinol, which has meta-hydroxyphenol, will interact longer with the stationary phase in comparison with benzene. So benzene will elute first without significant retention because it has no tendency to make interaction with the adsorbent, I mean the surface here, which is silica, whereas the other phenol, okay, can make hydrogen bonding with silanols. So we will end up with longer retention for resarcinol, and consequently we'll have separation between these two elements. Okay, even if we have phenol, such as cresol, when we have phenol with methyl group like meta-cresol. Now, definitely the one which has two separate hydroxyl group will retain longer in stationary phase. If hydroxyl group are near to each other, like catechol, when we have ortho hydroxyphenol, it will not retain longer in silica because the diol, in this case, in catechol, will be busy in intramolecular hydrogen bonding. So the silica consider catechol as more or less hydrophobic, even though we have diol, but the diols are busy with adjacent hydrogen bonding. When we have hydroxy in ortho position like this, they will be busy with intramolecular hydrogen bonding. Now, as you know, that adsorption from physical chemistry, that adsorption is surface phenomenon, whereas absorption is matrix phenomenon. So when we throw a piece of iron in water, this will be adsorption for water molecules over the surface of iron. On the other hand, if we throw, for example, a piece of sponge in water, this will be absorption ad, rather than adsorption. Okay, and I guess you remember Langmuir adsorption isotherm. This is one of the basic concepts of adsorption, that you can say that the adsorbent like egg box. Okay, when you have egg box, you have what? You have vacancies for the adsorbate. This is the adsorbent. Adsorbate is the molecule which directly bind with the stationary phase. So the eggs will occupy these spaces. This is just to simplify the idea of adsorption in order to be easily treated by mathematically. But in concept, in physical concept, that adsorption is simply reversible interaction, physical interaction between solid adsorbent, solid surface, and uh, solute. Solute might be in solid state, in liquid state, in gaseous state, whatever. So this is adsorption, and adsorption is the one of the important mechanisms in TLC and paper chromatography. So it is very good mechanism, contributed or highly contributed in normal phase separation. Partitioning, we discussed more or less all concepts related to partitioning. That partitioning, when we have the stationary phase as liquid and the mobile phase as fluid, either gas or liquid. So this kind of partitioning, when we have reverse phase silica, when we have modified silica with C8 or C18 hydrocarbons, then we consider the exposed surface of silica is liquid phase. It is hydrocarbon phase. So we have partitioning of analyze between mobile phase, which is almost aqueous, and the hydrophobic hydrocarbon on silica. And silica in reverse phase, if you remember, we said that it plays the role of solid support. So silica in reverse phase is solid support, whereas the real stationary phase is the group of hydrocarbons. Now we have ion exchange. We didn't discuss ion exchange in details. Okay, we just mentioned it when we talked about ion pairing. Now, what do we mean of ion exchange? Ion exchange, if we have, for example, water. Okay, now water contains calcium and sodium. Okay. Now, can we separate calcium from sodium? Yes. Calcium can make two interactions, okay, with anionic entities, whereas sodium can form only one. We can exploit this difference in order to separate this kind of electrolytes. So if we have polymer, now not necessarily that the solid support is silicon. Sometimes, especially in ion exchange, we use polymer like polystyrene cross-linked with divinyl benzene. Now, polystyrene cross-linked with divinyl benzene is one of the alternatives for silicon. This is polystyrene. This is styrene. Has phenyl with two carbon with double bond. Now we know that double bond is important for polymerization. When you have a guy here and another one adjacent him, if I have two bonds like this, then I can break one of them to make hand-to-hand attachment with my colleague. Okay, the same thing will be happen for monomers, that they break the double bond in order to make adjacent adjacent covalent bond, just single covalent bond with other molecules in the same. In this case, we will have polymerization for the polymer. Now, in such polymerization, we have a thread of polymerization. In order to make the polymer stronger, we need to interact these two threads of polymers. Like, for example, this one will make something like this. And so forth. So this is the polymer of polystyrene. This is a strand of polymerization. In order to cross-link it, you need an entities to be immersed in this thread and capable to form interaction with the next thread. One of the good candidates is divinyl benzene. This is divinyl benzene. It has double bond, upward and downward. We have this to make a thread, this to make a link with the next thread of polymers. Anyway, this kind of polymers is very good for stationary phase, particularly in ion exchange. And the idea that this polymer can be attached with negative anion with negative functionalities such as sulfonate or carboxylate. Okay, so when we have a stationary phase like this, sodium will make just one ionic interaction, whereas calcium can form two. So if we have continuous mobile phase, now sodium will elute first, then calcium, because calcium can form two bonds. If we have aluminum will be the latter, because it has three ionic interactions. Now we call this cationic exchange. Why cationic exchange? Because the analytes here are cations, so we exploit the name of analytes rather than the name of stationary phase. Although stationary phase has negative functionalities, we call this kind of mechanism cationic exchange, relying on the name of analytes. The same idea would be for cationic exchange. So cationic exchange should be what? Negatively charged, positively charged. Anionic exchange should be what? Positively charged stationary phase, like ammonium here. And again, anions such as Cl- or SO4-2 can be separated according to their ability to form ionic interaction. Now, observe apparently that a chloride will make just one of the ionic interaction, whereas sulfonate can form two. So again, we call this an ionic exchange, relying on the name of analytes rather than the name of stationary phase. You can use the same concept not only for electrolytes, but you can use it for molecules. For example, if we have a drug with just one positive charge and another with two positive charges, again, the one with one positive charge will elute before the former than the second one, which has two positively charged. So these, in general, are the mechanism of separation. namely adsorption, partitioning, cation exchange, anionic exchange chromatography, as well as size exclusion.